Okay, it's day 3, it's 12:45, and the next talk is an introduction to MEMS, and I have recently noticed that I really need this introduction because I have no idea what this is about. So please welcome the speaker, Jens Kaufmann.
Hi, my name is Jens Kaufmann. I'm a PhD candidate in Heriot-Watt University in Edinburgh, and I'm working in MEMS. And MEMS, I think just a few people know what it is, and so I thought it's probably interesting to ask a few questions in the beginning, not in the end. So what are MEMS? What kind of MEMS are they? How are MEMS made today? Why you will have problems to make this in your kitchen, or do you even want to make them in your kitchen? But what are the alternatives to make them if you want some MEMS? So what I can't give you is a substitution for a good book. My lecture on Introduction to MEMS was 2 years, so I think I can't cover this in 30 minutes. And I can't give you like a recipe or a workflow to make your own accelerometer or make your own gyroscope. But what I can give you is like a brief introduction in what are the key problems when you try to make very small structures. What are the processes you use for this today, or when you buy a product, how are they made? And what these products actually are. And which is, I think, the most interesting part is how we as hackers will be able to do them ourselves in the future. So MEMS is an acronym for Micro Electromechanical Systems. In Germany you hear mostly like microtechnology, Mikrosystemtechnik, MST, micromachining or microengineering. When you're in the English language, so they substitute this all the time, so take whatever you want. But what we're talking about is structures, devices and phenomena where the critical feature size is within the range of the resolution of light, visible light, and the millimeter scale. So here you can see several features or machines or beings you can find in nature on the top, and the length scale, like this is a colibri which is about 10-12 centimeters. Then you have a hair here which has a diameter of about 100 microns. Then what you see here, which is about 1 micron, are bacteria. Then you have a double helix, which is just assumed. It's not like it's actually looking. You can see it's computer generated, and a very easy abstraction of an atom, which is about 1 angstrom, which is 10 nanometers, 10th nanometers. And here you can see what we have today in technology. This is a piezo drive micromotor, a stepper. This is a gear with a coupling. You can see this is about 500 microns in diameter. And this is already nanotechnology. This is where Berkeley is quite good. What you see here are receptors for bacteria and the proteins they produce. So it's small, so what? The problem is when you change scales, that not all the effects are usually working with changing in the same way. It depends on the dimension they're actually using. So if you have magnetics, they have like 4 dimensions. So when you shrink them down, they shrink by the power of 4, which is quite rapidly. So what happens, and the gravity and the mass shrinks with the power of 3, electrostatics with 2. And this explains why you will find even piezoelectric effects. And this is why you won't find like a conventional DC motor on the microscale, because the magnetic effect weakens so fast that the electrostatic effect at some point is, when you get small enough, is bigger than the electromagnetic effect. That's what you always have to keep in mind. And the really bad thing is, like the van der Waals forces, they shrink with the power of a fourth. So that means that when you go very small, you have very big friction problems. You have a lot of stiction effect. So what you do is, for example, you have a cantilever, and this is touching the surface. This will never, ever go up again. It doesn't work. So these are some of the problems you're facing when you go there. But this is very theoretically. So, but what does it actually do, and how does an electromechanical system on a microscale looks like? This is a purely mechanical system from Sanjay Laboratories in America, a gear shift. It's made out of silicon dioxide, and this has like several layers, and it's made in a surface micromachine, which I'm going to explain later. This is a standard accelerometer, where you can see here there's like a cantilever with a seismic mass on the end. So when you move it up or down, this mass will always like be a little bit slower. It takes much longer to accelerate it, so it will bend, and then you measure the bending. But with this, you don't see any electromechanicals. This is purely mechanic, but what you can see here is a pressure sensor, and here you can see these are the embedded measurement structures. This is like a big membrane etched out of silicon, and here you have the sensors on the four edges of the membrane, which are then connected over aluminum. And so what you get is then basically a Watson bridge, where you can then read out the amount of how much the membrane is moving. But when you want to have a real system, you have to integrate it with electronics, because you want to have a standardized interface. You probably even want to have like already a file format, which is nice to have and easier than to implement afterwards. What you see here is a standard accelerometer from analog device. Exactly, it's a ADXL202, so it measures in the range of 2G in one direction. This is the actual sensor, and all the rest of this is CMOS, all kinds of stuff. So you have self-test, pre-amplifying, then resistor load, buffers, whatever you want. You can already integrate in this way. Sometimes it depends on the process you're using to generate the actual mechanical part. You can't do this. So what you do then is hybrid integration. So you have here the actual chip, which is doing all the calculations and stuff. And this is the microsystem here, over here, the mechanical parts. And this all is a ceramic carrier, which has embedded connections, so that you basically take the electronics part away from the mechanical part. And a few resistors, which is quite good to see how big they are. They are SMD. They are the smallest resistors you can buy, just that you get like a length scale here. What other MEMS are there? This is a little bit confusing, because in English you always, the most time they use the term MEMS for everything, even if there's no mechanical part involved at all, which is like this. This is a DNA measurement chip. They are basically just an array of electrodes which are fed out to the outside with a special coding that they can measure what it's actually doing and how much it is. Then MOEMs, which means micro-optical electromechanical systems. And this is a very good example, because you can buy products with this. This is a micro mirror array. As far as I remember, it's from TI. And what you can see is that there are a lot of small dots, and they're not just pixels, they are really like small mirrors, as you can see them here. This is like a bigger magnification of it. So you have here some kind of springs. Here you have the mirror itself. And all the mechanics, this is not the real color, how it looks. This is like colored afterwards. So what you see here is like aluminum sputtered onto the surface. Sputtering is some kind of deposition process. And all the rest is made out of silicon and then folded over. And this mirror, for example, is a different one than to the micro mirror array before, because this is able to move in 2 angles.
How big is that?
Wie bitte?
How big is that?
The pixel size here is about, I think the whole thing was here 120 microns. So this is about 80, I would say. And it's really nice, it's really nice. And this is something, as I said, you can't make in your kitchen. This is quite interesting for all the communication guys, because this is actually how it looks if you have a fiber hub, or if you have a good one, because this is a mechanical shutter for glass fiber. Yeah, and the fiber is about 500 microns. And what's quite nice here, this is self-assembling structure. So they're making that one, and then they flip a switch, and then it comes up by itself. It's done by, what's it called, electrostatic force. And then, yeah, there you go. Here are some RF, not quite yet MEMS. This is one of the processes we had just implemented in Edinburgh. This is a plastic glued onto a vial, glass vial, with some metal tracks. I think you can see them. And they are not like made in a conventional way. They're like laser direct writed. It's really nice, so you can write metal tracks onto plastics with the UV laser, if you're happy to have one. And these, if someone is working like with robots, you probably appreciate what this is. This is a transformer, a high frequency transformer made in Liga technology, so that you're up in the that you have a higher switching frequency, so you have less losses and so on. This is 5 pence, 5 British pence. These are some tweezers, so just that you get the whole thing is for, I think from here to here, it's about 10 millimeters, the whole transformer, and it has magnetic core. So this is quite nice. This is made basically out of 2 halves and then bonded together. Here are the connections for one winding, so they're continuous windings. Yeah, then you have many, many more different applications and structures for all kinds of problems. What I was showing was mostly so far sensors, because I know more about sensors than about actors. But you can have this for all kind of physical field you want. You can have it for mechanics, for thermal problems, even for magnetics. But I said this is really, really difficult, so you need meter materials, and you have to do a lot of material science there. But even in optics, they are like increased use of microsystems, because you don't need big structures for light. Light is very small, so it works quite good. And chemical receptors are becoming bigger and bigger. And especially biology is very interested in small structures, because then they can work with less hazardous material than they're used to. And this is always a nice thing to have. So what are the advantages of this? Yeah, if you have a specific problem in a specific size, then you try to shrink it and get rid of the problem. For example, if you have magnetic interferences in your part, and you can make it very small, then it doesn't matter anymore. And you have different problems like random tunneling electrons or something, but if you don't care, that's fine. Then you can make much more parts with very, very good processes, and so they're all batch processes. So if you have, like, you start up with a 3-inch wafer, which is about this size, and you get 100 chips on it, and or 100 microsystems, and you just go 1 inch bigger, and so you can do with the same process much more because it increases over the area with by the power of 2. Then you can, basically it's all about, we want to make it safe and cheap. So a few problems are still there. For example, detection. You can't, as I said, magnetic sensors doesn't work. So handling and integration is, when you have very small parts, you need very precise tools to work with them. Otherwise, you never will be able to make something like this. Or even, it's one thing to make it, but then put it in a package that someone else can use it. It's also a big issue in MEMS. And as I said before, friction is a big problem. And then what is it? It's very typical for, especially in like fundamental science of microsystems, is you have a microsystem which is about 500 microns altogether, and then you have a lab view set up next to it with 3 different computers, logic analyzers and stuff, and such a power supply, which is not really like, it's not what you want. But there are like a lot of research at the moment going on to like harvest energy from surrounding energy sources. Like RFID is one of the most famous ones, but you can also use like a special kind of accelerometer to harvest movement and make current out of it, or power. Yeah, this is like what MEMS basically are. And I want to show you 3 standard processes, 2 in silicon and 1 which is not in silicon. This is standard bulk micromachining. If you have a car with a wireless pressure sensor on all your tires, you will have something like this in it. So what you have is, you take a piece of silicon, put some silicon dioxide on top of it. Silicon dioxide is basically glass. So you can use chemical deposition, chemical vapor deposition. You can use magnetic enhanced chemical vapor deposition, but it doesn't matter. You put glass on top of it. Then you take a thin film resist, which is like a photoactive polymer, put it on top, structurize it with light, and then you have openings wherever you want the openings to the actual glass. And then you take HF and etch the glass open, and then you can use KO etch to structurize the material below. Because when you etch with HF, it will stop here on the silicon, it won't etch the silicon, and then you take KOH to shape basically the structure below the silicon. What you also can use is dry etching, like reactive ion etching, but this is something which is very, very, very expensive, and it's very slow, but you have really, really nice structures out of this. And why you use KOH is basically because you can get structures like this. So you, as I show you later, is that silicon is not etching in all the direction right away. So if you have like a piece of metal and you start to etch it, then you will have like a mushroom-shaped cutout, but you won't have this. You won't have this when you use silicon. Show later why. So you make an opening like this, and then you will basically under etch here the cantilever, and then you have a free cantilever. And this is accelerometer. Then the other one is surface micromachining. That works different. With bulk micromachining, you were like working on the material you have originally. When you do surface micromachining, you build up new structures on top. So what you first use is like silicon substrate. Then you grow with the same technologies than you use for the glass. You grow phosphorosilicate, and then the same again. You etch it, you structurize it, but then what you do is you take the silicon, the phosphorosilicate, you take away again. And then you have also like free structures, and with this you can make all kinds of moving parts. You can do micromotors, you can do gears, gyroscopes. Gyroscopes are normally using this technology because it's quite good to handle. This is a gyroscope, by the way. So this is surface micromachined and silicon, and this is a housing made out of Pyrex glass because it has a similar coefficient of thermal expansion so that you don't get any stresses in it. So, and this is the neat thing with silicon and why they still use it. Silicon is when you buy a wafer, which looks like one of those, it's like a normal silicon 3-inch wafer. They're actually made quite neatly. So they have a big beaker of molded silicon in there, and then they have an imp crystal and turn this all the time and slowly pull it out so that you get a big silicon sausage, and then you slice the whole thing to get these small wafers, and then you polish it that you have like defined properties on it. And because of this, you have the whole behavior is determined by the crystalline structure. It's just one crystal, not like glass where everything is like inside each other, how the nature made it. This is really engineered material almost, and so it's etching differently in different ways because there are like planes in the crystal, and it suddenly stops there when you etch something. And this is why you get this strange appearance, and you will always get this angle here, which you normally don't have in other materials. And these are like the planes you have in the crystal. But this is like, explaining this is a 3-hour lecture, so I don't want to bore you any further with this. And show you another process which was developed in Germany. It's LIGA. It's an acronym for Lithography Galvanoabformen, or lithography, electroplating, inkjet, not inkjet printing. No. What you do is injection molding. So you basically press a plastic afterwards in it, abform. That's what you're doing. And show you how it works. So normally you have a carrier and resist on top of it, and it's a thick film resist. Depends on the method you're using. You can use PMMA, acrylic glass, or SU8, which is really nice to handle resist. Then you structurize it, start the electroplating process, and grow over the structure. Then you remove the whole thing from the structure and start to press the plastic in it to reproduce the structure you had originally, which is very cheap because you can do a lot of them quite quickly, and it's standard technology. You can put this in any workshop and they will do it. So, can we do it too? Not quite yet. Few problems are there. The biggest problem is you need a clean room. This clean room, if it's stopping here, costs about €1 million just on air conditioning and temperature control but without the folks in there. If they go in there, it becomes more expensive. Honestly, when you're in a small clean room and you have 3 people there, try to be there at 9, because after 12 o'clock you won't get any good results anymore because of particle impact, and people are moving, so you get turbulences. It's really bad. So what they're doing is like laminar flow from the top to the bottom. So all the tiles you see on top, they are basically just like nets where they blow air through and suck it away here on the bottom. And also here, all the tables, they have holes that the particles can settle down and get sucked away. Yeah, why should you never hold a wafer like this? Because you can get contamination from top. So if you hold it that way, it's much harder to get particles on it. So when you check your wafer, you check it that way, not that way. Especially when you're wearing a beard. Big problem. And smoking. Smoking is really bad. When you smoke for the next 2 hours, you will really spit out large amounts, so like 10,000s per breath of particles bigger than 25 microns. They look like meteors in your structures. I have one here. This was just lying in a clean room, not in a clean room, for about a week. These are structures, they're fairly large, about 20 microns. Yeah, and this is dust. So, and as I said before, so normally you should have less than 1,000 particles, or there's something missing, per square foot in the clean room, bigger than 5 microns. And this is how big? 40 microns? So forget it. You will have a yield in your structures which is not good if you work like this in standard processes. This is a very old-fashioned pressure sensor. So you have the membrane on the backside and you etch from the backside, so you have to align here your connection structures to the backside, which is already a problem. And then here you will have small dotted areas, like with imprinted ions, so that you get like more or less electrodes in there, depends on what you're doing. And you have to connect them with the accuracy of repeatable 5 microns, which is really, really a big problem when you try to align this by hand, for example. I've done this, it works, but just once in a day. So it needs like 3-4 trials until you really get something out. You can do this in science, where you have like 3 years to do your project, which normally would take an industry 6 months. But it doesn't work if you have to pay for it. These are some kind of alignment structures. This is about the 10 microns, the width of the lines here. It looks a little bit like scratched. This is because it's in a foil. I never took it out, this one, so far. These are like the windings I showed you before of this transformer, but they're about 50 microns. That's also a problem when you use HF. HF is not a strong acid, but the problem is that it will just diffuse through your skin. You're not recognizing it, and the fluor in it will substitute the the calcium in your bones, and so your fingers start to wobble. You don't like that. And it's irreversible, so they will take your hand off. So be really careful if you ever try to mess around with HF. It's not nice. There's always hope, isn't there? And these are the first approaches. What you see here is a self-reproducing 3D printer from a guy named Adrian Boyer in somewhere in England. Not sure quite yet. It's relatively big, so microstructures won't work because the structures, the smallest feature size you can have is about half a millimeter so far. But fabbing is the way to go. Fabbing is basically desktop manufacturing. That means you have a box, and out of this box, and with a computer on it, and then you think about what you want to do. You make a 3D representation in your computer, and then you print it out. Or you get a BitTorrent of the new iPod and print it out. That's the idea. Yeah, what you're trying to do is like really make physical objects from digital representations. The mostly used, almost fabbing tools at the moment are rapid prototyping machines, and since 2 years there are like a growing community around 2 projects. One is Fab at Home, it's an American project which is not self-reproducing, and the RepRap project from England, which is more promising for us, because the nice thing on this project is if you have one, or let's say, you have one, then you can print out the next one. And if there's a revision like 0.2 point something, then you print out the revision and attach it to the old machine. It's really nice. And can show you what's already around. This is really, really, really impressive. This is from the Lasertag Institute in Hanover. These are photolithographic generated spiders, and they are 60 microns. So your hair is about that size. Just to give you some impression about the size. This is also quite interesting. This is a SEM picture of a selective laser sintered part from the Hochschule Mittweida. This is basically the same technology than used in the RepRap, just a little bit more accurate. And this is done on the University of Tokyo. And then you have also this Polymer Jetting, which is basically a modified inkjet printer, which is quite nice, but I haven't seen microstructures on it yet. But I think it's just a matter of time in the very near future. Because when you see how accurate printers are already today, then you can guess what kind of microstructures, 3D structures you can print then. I want to explain the more promising, or the ones where I've actually seen already microstructures on it in a little bit more detail. So this is how stereolithography works. So you have here some kind of piston which moves the elevator, and it will start up here, just below the surface, that you have like a thin layer on liquid photoresist on top, and then your laser comes, writes the structure on it, and it will photo cure it. So it uses the light energy to initiate a polymerization process and become stiff. And if it has done this, then it will go a little bit farther down and will write the next slice of your 3D structure. You need supporting structures, of course, but what they normally do to don't have like lumbers everywhere is that they like do it with a cone on top of it, so that you have a very small point of connection, and then you break it away. Next one is selective laser sintering, which has some advantages because you don't have to stick to the photo polymer. So you can basically use any kind of material you can heat up, and it will liquefy and then stick together. And this is what's happening here. So you have two pistons, and there's a lot of powder in there. So you remove the powder, you will move this piston a little bit up, so you get a certain amount of powder on it. Then you roll it over in the other one, which has like a small cavity here, and then it will fill it up until the top, and then you will write with your laser on it and basically weld it together. The advantage here is that you don't need supporting material because it will support itself, and then you take it out afterwards, take like a air jet and just blow it out, and your structure is done. And then this is again like the RepRap works. So you have a Cartesian robot, which is like working this in X and Y, and probably this in Z, or you directly have the Z on the nozzle. And these are two different thermoplasts with different thermal properties. So, for example, one will liquefy at 200 degrees, the other one at 400 degrees. So you use the 200 degrees one to make support structures and basically really extrude them out in lines so that you get your structure this way. And then you can extrude the other one on top, put it back in the oven about 300 degrees, so the support material will melt away, the other one will still stay. This is the other project, the Fab at Home project, which is really nice for future technologies because there's all the microsystems today are made by photolithography. So the mask you use for the initial structurizing is done by a photosensitive polymer, and you need a big photo lamp and a mask to basically do it, or a laser. And what this does is, this is like printing out the polymer just where you need it. And so you don't need the photo step. And then you can etch away, or you can grow something within the mold. That works really nice. The only problem is that this is too big right now, to not accurate enough to make actual MEMS. But it will become cheaper and better. What you can see here is a trial where someone was basically electroplating. So you have like a cathode and an anode and a solution of a metal salt. And then normally you switch on your current, and then the metal part of the salt will go to one way, and the other part goes to the other electrode. But what he does is like he is able to localize plate it and so make tracks on whatever you need. But you need a conductive surface. This is how electroplating, a scientific electroplating place looks. It's a current source, a beaker, a heater, and a stirrer. So this is something you can do in your kitchen, except of the sulfuric acid you need for it, smoking. Here's again the laser direct writing. And what's the neat thing on this is you can make it on any 3D surface. So you can make very weird structures. We're working at the moment on like folded structures and free forms. And this is really promising. And then there's powder blasting. Powder blasting is basically the same as sandblasting, just with smaller particles. And with this, the machines are about 4,000 pounds is 6,000 euros if you make it yourself. And then you can make an accelerometer without a problem. And this is something which fits very nicely in your garage. So what you basically have is an XY table with your nozzle, which blows out the powder, and you need a metallic mask on it. And this is normally done by a laser-cutted mask, but I can show you this later if you want. This is made out of normal PCB board, and normally they say copper doesn't work because it's like wearing off too quickly with the alumina, but this is like the hardest process we can run on this machine, and it's still sticked after 400 microns of digging into the PCB board. So that works fine. So you can do this with a laser printer, with an iron, and a powder blasting machine. You can make something like this. Yeah, and now the only question is, do you want to make your own steam engine? Thank you. Questions?